Hey there, this is Dr. Kofelt. This is part 6 of my lecture on chemical equilibrium. And in this part, we are going to do the most fun way, of calculating equilibrium concentrations when you just have the equilibrium constant and initial concentrations or pressures. So we're going to do this in terms of X, but this time, unlike in part 5, it is not going to be a perfect square because it's not going to be a square on the top and a square on the bottom. And so when it's not, then what you have to do is you have to use the quadratic formula. All right, and this is only when it's not a perfect square. Okay, so typically on my exams, I don't have one like this. I just do the perfect square one, because it takes a lot of time to do it, and a lot of people will totally run out of time on the test. So you will have it on homework if you're in my class, and you know, you show me that, and then on your homework and everything, you show me proficiency. Okay. Oh, and we're also going to do something called approximations, and that is if it's not a perfect square, but the k is really super small, like less than 10 to the minus 4 or 10 to the minus 5, then you can ignore the minus x when you're doing the initial calculation. So you don't have to do 0.2 minus x or whatever. So I'll show you how to do those at the end of this. All right. So just like we saw before, we have a reaction. It's 100 degrees Celsius. It contains initially NO2 at 0.1 molar. That's all you get. And it wants to know the equilibrium concentrations of the NO2 and the N2O4. And I'm just kind of reminding you of what the quadratic looks like. And so we have the beginnings of an ice table. And so our ice table, you know, again, you can do the Q if you need to. Most of the time they're going to be written like they're going to run, but you do need to do the Q if you're going to know for sure. So that's why I'm doing it for you. So the Q is going to be your NO2 squared divided by N2O4. All right, and so that's 0.1 squared divided by 0, which is technically infinity, or 0, right? Infinity, let's say infinity, because infinity is greater than 0.36. So it's proceeding to the left this time. Okay, so what that means is that since it's proceeding to the left, what that's telling you is that this is the one that goes up and this is the one that goes down. So that's the only difference, right? That's why you did the Q there, to see which way it was going. Oops, didn't mean to do that. All right, so this one is, so that means that this one is going to go up x and this one is going to go down 2x. So that's 0.1 minus 2x, and this one is x. And honestly, okay, so you can do the Q thing, but if you're given the information and you know one is 0 starting out and one has a concentration starting out, you pretty much know the one that you have some of is going to be the reactant. So you do Q to be sure, but if you have 0.1 of this one and 0 of that one to start, then obviously it's got to go towards the 0, which would mean it was going to the left. Just a tip. Okay. All right, so now we know which way it's going, so we know which way our x's are going to be. So our Kc for this, which is equal to 0.36, is going to be equal to 0.1 minus, let's see, 0.1 minus 2x squared, that just looks ugly, divided by x. Okay? Or another way of saying that is 0.1 minus 2x, right, times 0.1 minus 2x divided by x. Why did I do that? Because I got to do what? Think back from math class, because it's called FOIL. Yes, you're going to do a FOIL on it. So my sister's a math teacher. She loves it that we're doing this, because I say, you know, I finally found a use for factoring. Okay, because I never thought there was one. All right, so when I multiply that out, if you recall how to do the FOIL, it's, you know, that's outer, inner, and all that stuff, right? Not going to go through that, because you should already have that math skill. Okay, but that means that you're going to end up with 0.0100 minus 0.400x plus 4x squared divided by x. Okay, so I've got to get rid of that, so it's coming over here. So 0.36x equals 0.0100 minus 0.400x plus 4x squared. Okay, now once I get to that point, I'm going to change it into the quadratic formula. So the 0, and then I do that, it equals to 0, so that I can put it in quadratic form, is 4x squared minus 0.36x plus 0.4x is 0.76x plus 0.0100. Right? Yes. Okay. And so if you recall, from when you write it out like this, this is A, this is B, and this is C. And you need that, okay, because, and you keep the sign from whatever's in front of it. All right, and so you need that, because now when you use, so that's 4, that's a negative 0.76, and that is 0.0100. All right, you need that because now you're going to plug it into the quadratic. So when you plug that in, x equals negative b plus or minus the square root. I hear that Pop Goes the Weasel song in my head, because that's my sister sings that when she does this. Minus 4ac all over 2a, right? Okay, so I'm going up here. So x equals a negative of a negative 0.76 plus or minus the square root of a negative 0.76 squared, I ran out of room, shoot, minus 4 times 4 times 0.0100. Hope you can read that. Okay, so all that's together. So 0.76 squared minus 4 times 0.0100. And then all of that is going to be divided by 2 times 4. Start over here this time. So when I manipulate this under here, all right, then I'm going to get x equals 0.76 minus, plus or minus actually, 0.65 divided by 8. So I'll have two x's. One x will be 0.76 plus 0.65 divided by 8, which is going to be 0.176. And the other x will be 0.76 minus 0.65 divided by 8, and that's going to be 0.014. Because remember, I told you you're going to get two of these. So I got to look back and see which one of these makes no sense. The one that you know, it wouldn't make any sense. Neither one of them is 0, okay? Because if it was 0, that would be the one for sure. So I got to look at them. All right. So remember that x is the equilibrium concentration of the product. Okay, now I look back at the 0.1. If my 0.1 minus 2x, that'd be like minus 0.35 or something. Okay, well, there's no way you could have less than what you started with in your reactant. So if I was subtracting that from it, that would give me a negative, a negative number for my equilibrium concentration. So there's no way that one could be correct. See what I'm saying? If I plug that into x, the 0.1 minus, even if it was just 0.176, that would, be more than, that would be less than what I started with at the end. So that's why that one can't be it. So it's got to be this one as my x. So that means that my concentration of N2O4 is going to be x, which is 0.014 molar. And it means that my NO2 is going to be 0.1 minus 2 times 0.014. And that's going to give me 0.072 molar, and that one makes sense too. Okay, so you first see it's not a perfect square. You factor this, right? So you FOIL it. Then once you FOILed it, because it's 0.1 times 0.1, that's that number. Then it's 0.2 times 0.1, 0.2x times 0.1, and then 0.1 times 0.1, then 0.1, anyway, 2x times 2x. Okay, so inner, outer, whatever. Okay, so like I said, if you need to go back and look at it, go back and look at it. There's a quadratic section that you can look at. FOIL. This is called foiling, if you need to look that up. Okay, and you had to learn that in algebra, even though you screamed and they drug you while they made you learn it, because it had no relevance to the world, but now it does. Okay, it does in engineering too. So anyway, so our final concentration is 0.014 for the N2O4, and which we didn't make very much of it, did we? And we have 0.072 left over in the NO2. Aren't those fun? Okay, so I gave you a practice. Okay, here's your practice, and it's like the concentrations change because we changed the temperature. And there's another practice. Okay. All right. So sometimes it saves us if our K is, oh wait, before I do that, sorry. This one is the same kind of problem, except you're using KP instead of so instead of molarity, you're using the atmospheres. And I'm going to look at this one, and I'll tell you what, you can look at one and tell if the concentrations of these two are the same, and you've got two of the product, it's going to be a perfect square. Okay, because it's going to be, the reactants are going to be squared, and the product is going to be squared because it has the coefficient. So I'm gonna do my ICE table for this. So ICE. All right, and so I have I2 and Cl2 and ICI, and I have two of those, one of those, and one of those. All right, and so these two are 0.1 initially, so that one's 0. All right, so I know which way it's going to go, right? Okay, it's got to go to the right because that's the one that I don't have any of, so that's what I'm making. All right, then I don't know what the change is, so I know, since I know it's going to the right, and you got that right, because if you have 0 to start with this one, that's got to be the way it goes. All right, so then that means that's minus x, and this has got 2 moles, so that's plus 2x. So 0.100 minus x, 0.100 minus x, and 2x. Right? Oh, wait. I already had some of this. My bad. The PICI was also 0.1. So everything was 0.01. So, sorry. So this one's, I wasn't looking at it right. It's minus 2x. Plus 2x, sorry. Okay, sorry. I didn't look. See, I didn't read like I tell y'all to do. So the partial pressure of the I2 is 0.1 atmospheres. Chlorine is 0.1 atmospheres. And then ICl is 0.1 atmosphere. So everybody's 0.1 atmosphere to start with. So that's what my equilibrium concentrations are in terms of X. And I already figured out it's going to the right. And I told you how. So if you missed that, go back and review it, because then you don't have to do the Q calculation. You can. Okay, you can. All right, so I'm2 Kp equals partial pressure. I'll write it like they tell you to. Ci squared divided by partial pressure of I2 times partial pressure of Cl2, which is going to give me 0.1 plus 2x squared divided by, and those are both the same, so divided by 0.100 minus x squared. So since they're square on top and square on bottom, they are a perfect square, and that's equal to 81.9. Okay, so the square root of 81.9 is equal to 0. I'm just taking the square both sides, right? Is equal to 0.1 plus 2x divided by 0.1 minus x. All right, so I got to get rid of this on the bottom. So the square root of 81.9 times 0.1 minus the square root of 81.9 minus x, sorry, is equal to 0.1 plus 2x. All right, so I need to combine like terms. So I want all my x's on one side and I want all my numbers on the other side. So the square root of 81.9 times 0.1 minus 0.1, took that from that side, equals, and that one's going over there, equals 2x plus, because that was a negative, so the sign changed, square root of 81.9 times x. So 0.905 minus 0.1 is equal to 2x plus 9.05x. So 0.805 is equal to 11.05x. X equals 0.805 divided by 11.05. That equals 0.0729 molar. All right, and so the concentration of I2, or I'm sorry, the partial pressure of I2 is the same as the partial pressure of Cl2, and that's going to be 0.1 minus x. So 0.1 minus 0.0729 equals 0.0. Ooh, didn't mean to do that. Sorry. 0.027 atmospheres. I got all excited. Sorry. And then the partial pressure of the ICL is equal to 0.1 plus 2x. So 0.1 plus 2 times x, which was 0.0729. So that is going to give us 0.246 atmospheres. Right. So the partial pressure of the iodine and the Cl2 is going to be 0.027 atmospheres, and the PiCl is going to be 0.246 atmospheres. Right, so this one was a perfect square. Just remember, when it's a perfect square, you can do it by the rule of squares. So taking the square root of both sides. If it's not, then you have to use the quadratic formula. Fun. So sometimes if it doesn't meet the rule of squares, then we can use what's called an approximation. And the approximation basically means that the approximate value of x is going to be less than 5% of the initial concentration. All right, and like you, basically if the initial is 1,000 times greater than k, you can use approximation. Okay, so I'm going to show you what that means. So in this case, I have 10 to the minus 7. Okay, so 1.67 times 10 to the minus 7. And I have 0.0125 and concentration per 0.5. So really, remember how important it is that you do this when it's telling you moles. So the molarity of this is 0.0250. 0.0250. So when I look at that, 10 to the minus 7, okay, is what we call very small. And you might see me say that. The Kc is very small in relation to the concentrations. So since it's very small, that is, it's 1,000 times smaller than what we're doing, we can use what's called the rule of approximations. So my initial, and I'm doing this for you. You got to remember to do this though, to always look and see what your volumes are, because if you just read through this and said 0.0125, you would be off. You'd be half as much as you were supposed to be. So 0.0250. All right, and so we have 0. We have 0 for these, so they are the product. So that means that I'm going to go down with my H2S, and it's got 2 moles, so it's minus 2x, and my H2 is plus 2x, and my S2 is plus x. So my equilibrium concentration for this one is going to be 0.0250 minus 2x, 2x, and x. All right, and that don't look like a square, so oh no. All right, so Kc, which is equal to very small, 1.67 times 10 to the minus 7. Like I said, in most problems, if it's 10 to the minus 5 or smaller number than that, you're going to be pretty much good to go with approximation, okay? All right, and remember, I told you I'm not going to give you one that is a quadratic. So if you, on the test, you do have to do them in homework, okay? Because I got to know that you can do it. But in the interest of you having enough time to finish your test, you're just going to be doing these others. 1.67 times 10 minus 7 is going to be equal to 2x squared times x divided by, there's a lot of x's on this, 0.0250 what? Minus 2x. Stop doing that. Okay, that's ugly. Oh, and that's squared. But that's not a perfect square, right? It's not. So, but it is very small. And so what that allows me to do is when I am calculating this, if I have something that's subtracting the x, I can approximate that that is basically 0 because it's not really going to change that number. Because 2 times 1.67 times 10 to the minus 7 is 3 times 10 to the minus 7. So 0.0250, let me show you. 0.0250 minus 2 times 1.67 times 10 to the minus 7 is still going to be 0.0250. So that's why I can use approximation for that. And I don't have to go through all that extra math because it doesn't make any difference anyway. Now, if you're anal about this, and I guess that's an okay word to say, and you really want to do that, then you can work all of them with quadratics. So if you are a math genius and you like it, then and you can do it, quick enough to get through the test, you can do a quadratic on all of these. But I'm just telling you how to avoid it. If you're like me, you want to do it the easiest way, right? So I'm going to use the approximation on this, which means when I do this calculation, I'm really going to do it as 2x squared times x divided by 0.0250. So I'm leaving this minus squared. So I'm leaving that minus 2x off of there. Okay, so and then that's also equal to, and make sure you do this right because this whole thing is squared. So that's like 4x squared times x, which is 4x cubed, divided by 6.25 times 10 to the minus 4. That's 0.0250 squared. All right, so 1.67 times 10 to the minus 7, which is KC, I forgot all about it because I was doing all that other stuff, is equal to 4x cubed divided by 6.25 times 10 to the minus 4. So I got to multiply that over there. So 1.67 times 10 to the minus 7 times 6.25 times 10 to the minus 4 is equal to 4x cubed. Now remember, when I was doing perfect squares, I had to take the square root of both sides. Now, since I have a cube, I'm going to have to take the cube root of both sides. So cube root and cube root, right? Now, I probably need to get, before I do that, because that's what I'd do, I'd be going, oh yeah, take the cube root. You got to get rid of this 4 first. Okay? So I'm going to erase this, and you probably haven't written it down yet. So anyway. So I'm just going to go back through this. So the 1.67 times 10 to the minus 7, which equals the 4x times 6.25 times 10 to the minus 4 is equal to 4x cubed. All right, so before I get all crazy and start doing things, I've got to get rid of that 4. So I divide both sides by 4. So 1.67 times 10 to the minus 7 times 6.25 times 10 to the minus 4 times, no, divided by 4 equals x cubed. Now that I've just got x cubed, and I can take the cube root of that to make that x, and that'll give me x if I take the cube root of the number side. So I'm going to take the cube root of this and the cube root of that, and so that's going to give me x over here, and it's going to give me 2.97 times 10 to the minus 4, which is the cube root of this whole thing right here. Okay? And again, your calculator can be your friend or it can be your worst enemy. So make sure you know how to use it. All right, so the concentration of H2 is equal to 2x. So 2 times 2.97 times 10 to the minus 4 is going to be 5.93 times 10 to the minus 4 molar. The concentration of S2 is equal to x, so that's going to be equal to 2.97 times 10 to the minus 4. And then the H2S, when we get done, is equal to, now you got to use that X when you go back. So 0.0250 minus 2X equals 0.0250 minus 2 times 2.97 times 10 to the minus 4. That's going to give you 0.0240. Now, it did change a little bit, didn't it? But it is close enough, okay, that that approximation is okay. All right. So if I tell you that it's very small, or if you see it's negative 19 or something like that, it's totally okay to use approximation. All right. So those are your concentrations. Oop. Okay. Isn't this fun? I promise the next section will actually be fun. All right. And so you have plenty to practice in this part. That's why I'm keeping them short and sweet. So go back and work these problems. Make sure you can get them done.